All right, it is officially 12:30, so let's go ahead and get started. First of all, I know on Friday there's a little bit of confusion about orbitals, how to draw an atom. So over the weekend, I made like a supplemental less than 10-minute video with some slides to accompany it and posted it on the Google folder and the YouTube channel that I post the recorded lectures. So if you have questions about that, go ahead and watch that video. I'm hoping it like clarifies a lot of things, but if it doesn't, let me know. So that's why I have this supplemental lecture is posted online. It's like every other time this works, but it helps if I turn it on. All right, maybe not. All right, so last Friday we kind of left off with this review question that we kind of skipped over because we ran out of time. So I want to start with a very similar review question. All right, so I want you to work in groups. I understand that we've shifted spots a little bit, and that's totally fine. So I will come through and just make sure we're all still in a group. I want you to look at this molecule that I have up top here and determine, is it polar? Is it nonpolar? And if it's polar, predict which atom is going to be where the electrons are going to be the closest. Which one has the highest electronegativity, which one hogs those electrons. So I'm going to give you about 2 minutes just to kind of discuss this quickly, and then we will review. Oh. I want my timer start. Maybe if I physically press it. There we go. All right. So we're still in group of 3 here, right? Right, why don't I have you work with me over here? Yes. All right, so that was 2 minutes here. So let's come back together and go over these answers. So if we're looking at this molecule, what do we think? Is it polar or nonpolar? Polar, yes. Why did we say that? Yeah, different electronegativities. They're going to be sharing those electrons unequally. Which one has the higher electronegativity here? Sulfur, yes. So where are the electrons going to be hogged closest to? Sulfur, yes. And I will point out that this molecule, if we look at hydrogen and sulfur, they're pretty similar. And so this would be considered a very weakly polar molecule. Right? It's not like we're bonding these hydrogens all the way up to these oxygens, but it is still polar. Any questions? Yes.
Yeah. What's the scale on electronegativity? Like how weak is considered weak when it comes to the difference in electronegativity?
Ooh, that's a great question. I don't know the threshold for covalent bonds. So I know if we look at molecules that just have C and H, right, those are close enough that we consider it nonpolar. But sulfur and hydrogen, it's just a little bit more electronegative, and we consider that to be a covalent bond. So I'm not sure what the threshold is. I'd have to look that up. I know for ionic bonds, it's something like if it's over 2, they'll be really attracted to each other. If they're under 1.7, not so much. Great question. Do you have any other questions? Yeah?
I don't know if this is something that you said, why is carbon negative?
Yes. That's a very good question. And it is very simple. I don't know why. For whatever reason, sulfur to hydrogen is considered polar. It might be something to do with the arrangement of the electrons in the orbitals. That would be my guess, but I'm not positive. It's very weakly polar, though. Right? So it is polar, but very weakly so. Yeah. This one was meant to be a bit of a tricky one. But everybody kind of pulled up on the fact that it is polar. I was expecting some of you all to expect it to be non-polar because it was so. Some great discussion. I love it. I will have to look up these answers for you. All right. Let's see. I will get this to work one of these days. Let's plug it into a different slot. So we're going to look at more chemical bonds today. All right. So we already went over covalent. We did some great review. It sounds like you all have a really good grasp on it. I know there's some nuances and the electronegativities here, but you're picking up on those big concepts that I want you to grasp. So we're going to move on to the other two bonds, and we're going to start with these ionic bonds. All right, so if we're looking at an ionic bond, we're looking at ions. All right, so ions are atoms that have a charge because they've either lost or gained additional electrons. So if we look at this example of sodium up here, all right, we have our sodium atom, right? It's going to lose this electron in the outermost electron shell, and now becomes a sodium ion that's positively charged, right? Positive because it's lost an electric or a negatively charged electron, right? So it's becoming positive. So that would we would call it a cation because it's positively charged ion. The opposite would be true for, say, this chlorine atom down here. And so for this chlorine atom, right, it's actually going to gain an electron, right, adding it into this atom, making it an ion because it's gained a negative charge. The overall ion is now negatively charged. All right, so we have gained an electron here. We have lost an electron here. Right? We're playing around with those charges. Those charges are no longer equal between the proton and the electrons. So now the overall atom has a charge to it. Okay? Now some atoms are more stable this way. Right? So atoms, they like to be in this stable state. And they're the most stable when their outermost electron shells are filled. Right? And so if we look at this sodium atom, we see we have one single electron in that outermost electron shell. That electron shell is definitely not filled, right? And so in order to get to a stable state, this sodium ion is going to let go of that electron, right? It reduces the number of electron shells it has to 2, but that outer electron shell is full, right? That makes this atom very stable in its ion form, right? So oftentimes you're going to see atoms not written as like sodium like Na, you'll see Na plus because that's when they're the most stable. Yes, Max. Sodium.
Oh, it's
Yeah.
sodium.
There are many, many more examples. Yes. And sometimes, for example, calcium down here is also stable as an ion. but it has a 2 plus, right? Meaning it has lost 2 electrons to become stable. So it can lose or gain more than just one. Do you have a question, Eddie? I just answered it. Great. I love it when I do that. Any other questions about ions? All right, so now have these atoms that have a charge associated with it. Right? I keep forgetting this doesn't work. And so when we have these ions that have these charges, we know opposite charges attract, right? They have these opposite charges and they are attracted so much that they're going to stick close to each other, creating an ionic bond, all right? And so this is where a cation is going to stick close to that anion. We're getting that ionic bond forming because of the differences in charges. And typically how this might happen is we might have 2 atoms, like sodium and chlorine, right? If the sodium loses an electron, which it likes to do because it wants to become a stable atom, it'll donate that electron to the chlorine atom, making it a chloride ion, right? Now notice these electrons are not being shared, right? One atom is giving up its electron and giving it to another atom. So unlike covalent bonds where they kind of shared those electrons, right? This is not the case here. They are not sharing them at all. Right? So those opposite charges attract them together and we create an ionic bond. Right? It's a little bit simpler to understand than maybe covalent bonds. Right? We don't have to look at different electronegativities per se. So I like this diagram that's in that textbook that if you bought, great, you didn't, that's quite fine. But I like this diagram here because it shows you between covalent bonds and ionic bonds how these electrons are being shared or given away or accepted by each of these molecules. So if we look at these covalent bonds down here, it's nonpolar. They're sharing electrons, and that sharing is very equal. Right? If we have that polar covalent bond, all right, again, they're sharing electrons, but it's an unequal sharing. It's going to be closest to this atom with the higher electronegativity. Yes?
So determination between whether or not a bond is created by equal sharing or transformation by the electronegativity. So like if the 2 atoms have like widely different, like they go from polar like unequal sharing
Not to the complete trade-off. So we're talking covalent bonds. We're sharing these electrons, right? We're not totally giving them away. And so the electronegativity definitely determines whether or not that bond is going to be polar, right? But now if we have these atoms that, in order to be stable, will be in this ionic state, or this ion state, right? And we eventually just completely lose an electron or completely gain an electron, right? When we have those types of atoms, that's when we get this ionic bond. There is electronegativity that plays into it. I'm not going to introduce that concept for this class because I think it's beyond what I want you to know. But it's that completely giving away and it's conceding of electrons. Does that answer your question?
Yeah, so ionic is more stability.
Yes. Yeah, that's a great way to put it. Yeah. You would know by looking at their arrangement and their electron shells. You would probably need to know that more in chemistry. If I want you to know if it's an ion or not, I would tell you. Yeah. I don't expect you to memorize all that for Bio 101. Any other questions? These are great questions. All right. We're like at the very bottom of Bio 101, so lots of these little nitty-gritty details here. So that last bond, right, is going to be a hydrogen bond. And a hydrogen bond is different in that typically it's going to bond different molecules together. Right? So in this image up here, we have our water molecules, right? And they are being bonded to one another by these hydrogen bonds. Right? So these hydrogen bonds occur in these polar molecules, right? Molecules that have a partially negative and a partially positive charge to them. And the hydrogen, because it always has this really, really low electronegativity, is always going to be partially positive. So this partially positive end of our molecule is going to be attracted to the partially negatively charged end of another molecule. Right? So it's those hydrogens driving the bonding here. Right? Now this bond is typically the weakest of the three that we'll talk about. Not to say that it's a weak bond, but it's the weakest of the three bonds. And it can be easily disrupted. Right? We can also see hydrogen bonds occur within molecules. And we'll talk about this when we talk about 3D structure of molecules. So if you have a really, really large molecule, right, this is one very large molecule, much larger than water, right, we can see within the structures, we can have some hydrogen bonds going on between these differing polarities within a molecule, right? Yes? Yes, yes. It's that partially positive charge of that hydrogen that's driving these bonds. Yeah. All right. So I'm going to take a step back and we're going to focus on our water molecule because that's what the rest of the lecture is going to be on here. I want you, again, in those groups that we have already formed here, let's look at the water molecules. Answer these questions. They should be relatively easy to tell apart, but this is a great time to ask more questions if you have them, and then we'll come back together with the answers. Unless you watch my slides carefully, and then you can probably see the answers. There we go. We have answers to our questions. That's what creates that electronegativity. I mean, that's like the term for this concept. Yes. But they have to be on so it's where the hydrogen is bonded with the oxygen. That's our fluid. And that hydrogen is bonding with oxygen of another molecule. That would be I don't know, the word hydrogen bonding, I think this is throwing me off a little bit. Covalent bonding is with one of the water molecules. The oxygen and the two yes, the other one.
Socialize.
That's a great way to put it. Socializing. I like it.
She's a color covalent.
Yes.
But when like when
Yes, I like it. All right. So let's come back together here. I know there might have been a little confusion. I liked the wording we used over here that when we're hydrogen bonding, we're socializing with other water molecules. I think that's a great way to think about it. So what bonds do water molecules have? The molecule itself. Just thinking about one of them. Yep. Covalent, yeah. And particularly, is it polar or non-polar? Polar, yes. A polar covalent bond. So that makes the entire water molecule itself, is it polar or non-polar? Polar, yes. And then what bonds connect the water molecules together? Hydrogen bonds, yes. All right, so I included this slide on here. I'll leave it up for a little bit here. All right, it's like covalent bond is the sharing of electrons within a molecule, what allows a molecule to become a molecule. Right? Water is a polar molecule because oxygen is more electronegative, so it hogs the electrons. And if our water molecules want to socialize and interact with each other, all right, now we get the hydrogen bonds forming because of the polarity of the single water molecule itself. Good? Any questions on this? I don't want to move too fast because I know I had multiple spots where you need to fill in the covalent bond. Water is a polar molecule, and hydrogen. All right. So I already asked if you had questions, but again, if you want to ask a question and want to remain anonymous, there is that link up there for you. So the rest of our discussion today is going to be about water, because water is just a hugely important molecule here on Earth. All right. The structure and the properties pertaining to the structure of this molecule just make it such a good resource for pretty much every organism to utilize here. So we want to talk about water, and we want to talk about these properties of water that make it such a good resource. So first of all of these properties of water are because water is polar. Right? The polarity of this water molecule is deriving all of these properties. And we're going to go through these one by one here. I did put a link up here, YouTube link if you like cartoon versions of things. That's a great video to watch. Yes.
is this property properties
Yes and no. Depends on the molecule. I'm going to say water is really great in that it has all of these properties happening all of the time. Yes. But I would imagine, I can't think of another molecule off the top of my head, but other polar molecule to polar molecule interactions will have some of these, I'm sure. Just maybe to varying degrees. So we're going to talk about water as a solvent. All right? Water is a great solvent. It is such an excellent solvent. And so to talk about a solvent, we have to learn a few different definitions. So if I say a solution, right, you'll hear there's a lot of math. Obviously, a solution, right? A solution is solutes in a solvent. The solutes being the dissolved substances, and the solvent being the liquid, right? So when we have something dissolved in a liquid, we have a solution. So those solutes, dissolved substances, solvent is the liquid. And if that solvent happens to be water, we would call it an aqueous solution. Right? And where water is the solvent, it makes for a really, really good solvent. Right? And I will add that most things that dissolve in water are going to be molecules that have some sort of a charge associated with them, whether it's ions or polar molecules. All right, so let's talk about how something would dissolve. All right, so we have this man here. He is eating. I've been trying to figure this out. If you know what he's eating, please let me know. I thought it was French fries. It looks like there's ketchup and some salt there, but I don't know who eats French fries with a fork. Good question. But he is eating something salty and drinking some water. That salt is dissolving in the water. And why water is such a good solvent? Again, it has to do with its polarity. So salt is sodium chloride, right? NaNaCl molecule. And they are normally ionically bonded together, right? But when they enter in a solution with water, those water molecules, because they are polar, are going to surround these charged atoms, right? So if we take a look at sodium here, it's positively charged. Now, oxygen of the water molecule, we know has a partial negative charge. So that negative charge is drawn to that positive charge, and these water molecules will start to surround the sodium molecule. Okay? And they start to surround it so much that they will disrupt the bond between the sodium and the chlorine, okay? Thus disassociating them, breaking that ionic bond, and they are thus being dissolved into the water. So the same happens for this chlorine atom here, just in an opposite way, right? Chlorine is negative, or I should say chloride is a negative ion here. We have the partially positive charges of our hydrogen being attracted to that negative charge, surrounding it, breaking apart those ionic bonds, and dissolving it into water. All right, so polarity of water makes it super easy to dissolve these substances. And it's such a great solvent that we have these terms associated with molecules in regards to water. All right. And so if we say a water molecule is hydrophilic, it means it's water loving, right? It's something that's going to be easily dissolved. And these are going to be such molecules that are maybe ions, right? Or that have some sort of a polarity to them. They will easily dissolve. They are hydrophilic. Versus hydrophobic, and I think this is an easier one to remember because if you have a phobia, you have a fear of something. These are these water-fearing molecules, right? They do not dissolve in water. So think of like an oils in water. That's a great example of something that doesn't dissolve. Most of these molecules will be non-polar, right? And then we have these molecules that have a little bit of both, right? They have a polar region to them, and they have a non-polar region. We would call them amphipathic, meaning they have both loves, right? They love water, they also hate water. Oftentimes when we get these type of molecules, right, so for example, each one of these blue circles with the white squiggly line is our molecule here. The blue circle is the polar region of the molecule, right? And it's polar, so it is water-loving, it is hydrophilic. Versus these long squiggly ends, I'll call them the tails here, right? These tails are water-fearing, right? They are non-polar regions. When we get a group of these molecules together and say we put them in water, they tend to form structures similar to this mycel structure here, where all the water-fearing ends will come together, and all the water-loving ends will be on the outside and actually interacting with the water. All right, so there can be some complex interactions with water here. All right, I'm trying something new. I've never done a class poll like this before. But if you have a phone, take, let's say, 30 seconds to answer the question, and we'll pull up the results. I meant to put the question on here. I believe I'm asking whether a molecule is hydrophobic, hydrophilic, or amphipathic. These are real-time results, which I don't know, I think is pretty cool. Looks like we have the majority of the class answering here yes. So a polar molecule is hydrophilic, meaning it will dissolve in water because it has a charge associated with it. Do you have any questions on water being a solvent? All right, I know this is like a really content heavy day, so I apologize. All right, so we're going to go on to the next property of water. And this property of water has to do with how water changes states, right? So we can find water in 3 different states: as a solid, as ice, as water vapor, as gas, or as water, as a liquid, right? Now, in order to change between these states, there has to be some sort of an input or release of energy, right? Now, this input or release of energy typically comes from bonds breaking apart or reforming, right? That's either going to give the molecule energy or release some energy, right? So when we want to change the state of water, right, an important term to know is what's called specific heat. So this is the amount of heat energy to raise the temperature 1 degree Celsius. Right? Water has a very high specific heat, meaning it takes more energy to raise water 1 degree Celsius than maybe a different type of liquid. Right? So we need to put in a lot of water to get our water to boil to eventually form that water vapor. Right? So water uses a ton of energy. And it's the hydrogen bonds that are really important in this, right? So we have that hydrogen bonding going on, right? And so if we have energy associated with molecular movement, we can say that's heat, right? So in our solution of water here, we have these water molecules constantly forming and reforming bonds. As we increase the heat, those bonds are going to become more and more unstable and want to not form as readily with each other. Okay. We can measure that intensity by taking the temperature. So if you've ever watched water boil, right, maybe you're boiling some water for pasta, right? And you might not have a thermometer, but if you put your hand close to that water, you can feel the temperature increasing. Right? Water has to absorb just a ton of heat in order for it to boil. And this is great, right? So we know water boils at 100 degrees Celsius and 212 degrees Fahrenheit, right? It takes a lot of heat to get water to boil. If water boiled, say, at 50 degrees Fahrenheit, that'd have radically different implications for all the organisms on the planet here, right? If you go swimming in a lake in the summer, sometimes the lake temperatures can get into the 50s. If we didn't have a high specific heat and water boiled at 50 degrees, we would have no lakes, right? It would all boil away on us. That wouldn't be great. So water has a really high specific heat. It takes a lot of energy for it to change states. These are probably terms you're more familiar with, is that water has cohesion and adhesion. Right? So cohesion meaning water molecules are very attracted to one another via that hydrogen bonding, but also adhesion, and that they're very attracted to other surfaces, particularly if those other surfaces have a charge associated. All right? So basically, water molecules, they want to stick together. They also want to stick to other surfaces. And we can see this in action if you've ever tried to pour out a glass of water and it does not pour cleanly. It starts running down the side of the glass, makes a huge mess on the counter. All right, that's those cohesive and adhesive properties at work. Right, we have the water stream, so the water is being held together. They're very cohesive, but they're also trying to be adhesive to the glass itself, which is why water's trying to cling to the glass before it falls. It can also be very important in a lot of plants, right? Well, almost every plant. In that these cohesive and adhesive measures, it's what drives water from the soil all the way up through the trunk of a tree and out the leaves, right? If water was not cohesive, trees would have a really hard time pulling it up because the water molecules would not want to stick to each other. Now, these cohesive and adhesive properties are also important for the last two properties of water that we will talk about. Water has high tensile strength, right? So if you're testing the tensile strength of something, I like this image up here because it's showing that you're pulling on opposite ends, right? You're trying to pull something apart, essentially. If it has a high tensile strength, it does not want to pull apart, right? And so because water is so cohesive and likes to stick together, it also has this high tensile strength. It takes a lot of force to break a chain of water molecules apart. Right? You can see this if you fill a cup too full, or in this case, they put a drop of water on a penny, and you can see that drop of water is kind of domed over the penny. Right? The water does not want to break apart. It wants to adhere to each other. So it's forming this dome until the pressures are just too strong and we finally have enough energy to break some of those hydrogen bonds. But it takes a lot, right? It has this high tensile strength. But it also has a high surface tension because of being cohesive. Right? Water molecules, again, they don't want to break apart. So certain insects, like this water strider here, have the ability to walk on water. Right? They are light enough to walk across these water molecules without breaking those hydrogen bonds, right? Because those hydrogen bonds are so tightly cohesive with all the water molecules there. Do you have any questions about any of these properties? There's a lot of technical terms here. Yes? Ooh, I want to say it's the bonds. So in order to break apart the bonds, you have to have some sort of input of energy to break it apart, and I'm thinking certain bonds might have different requirements. I'd have to give you a more precise answer in a bit. That's another great question. I like it. So, water is great, right? We use water for everything. It can provide support for plants. It can participate in chemical reactions. We'll see that on Wednesday. Can remove toxic waste components, particularly in our own bodies, the kidneys, right? Removes a lot of those toxins. Evaporative cooling, right? So if you've ever gone swimming in the summer and came out of the pool and you were cold, even though it's hot out, right? It's all those water molecules evaporating off your skin and taking heat away with it, right? A lot of organisms, especially desert organisms, really utilize this. We have cohesion and adhesion, surface tension, and water is also a great lubricant. Saliva is a great example of that. So a lot of organisms have saliva to help lubricate when they eat their food. All right, so I want to do a quick review here. We actually have 4 minutes, so not a super quick review. But I want you to think about all these properties we just talked about. If water was nonpolar, how are these properties going to change, right? And if water was nonpolar, what implications do these change of properties have for these various organisms on Earth? Right, so take 4 minutes, talk it out, ask me questions if you need clarification on anything here. Actually making good time. A little nervous. I know. I think I want to start my timer, but I hear conversation shifting and it's getting a little quieter. So let's come back together. So how are these properties of water going to change if water was nonpolar? What would change about these properties? Yeah, we won't have any hydrogen bonding because we need polarity of our water molecules, the hydrogen bonding to occur. What else? Yep.
You either have a lot more or a lot less ice.
Yeah, definitely. You might be able to change states of states of matter a little bit easier to react with them inside. Yes. So basically, all these properties are going to change, right? Every single one of these properties are reliant on water being polar. And if water is nonpolar, we're in for a lot of trouble, right? So if we're thinking about how might this impact organisms on Earth, we said we might not have trees. Right? Trees need to draw water up through their trunks, and if you don't have trees, you have a lot less oxygen. How else might organisms be impacted?
Well, into the lack of
Yeah, it would change how well it dissolves something. So if we eat, right, we're not going to have that saliva or water in our saliva to help lubricate what we're eating. Yeah. There's so many implications. Pretty much the world as we know it would not exist without water. That's how hugely important water is as a molecule. I just have a couple more slides here because I wanted to touch on pH because pH has to deal with water, right? And so in a aqueous solution, a solution of just pure water, some of those water molecules will break apart, right? And form hydrogen ions and hydroxide ions, right? So at any given time, there's going to be some water molecules that are broken apart. Now, if we dissolve substances in water, right, we might have compounds that, when dissolved in water, are going to release more hydrogen ions, right? And when they do so, we call that an acid. So changing the concentration of hydrogen ions. The opposite would be true if that compound is dissolved in water and now it accepts hydrogens. That would be a base, right? So when we're adding in these different solutions to water, we're changing the relative amounts of hydrogen ions and hydroxide ions to each other. And that can change this pH of the solution, right? The pH of the solution totally depends on how many hydrogen and hydroxide ions there are. I really like this image here because it gives you a sense of how this works. So if we add a very acidic solution like lemon juice into water, right, it's an acid. It's going to release more hydrogen ions. And now we see that the relative concentration to hydrogen to hydroxide has changed. There's more hydrogen ions. It's an acidic solution. Right? Opposite is true with a basic solution. Say if we added bleach into water, right, it's going to accept some of those hydrogen ions. Right? Again, changing that concentration, so we have more hydroxide ions, making it a more basic solution. And there's many different effects of pH. Right? I'm not going to walk through these because I want to give you a homework assignment. Right? This homework assignment is due on Friday. So you have some time. It's a content check. It should be relatively straightforward. It shouldn't take you too long to do. It's on Moodle. I want you to either type in your answers or print it off and write in your answers. You will hand this in on Friday, and we will go over this together. All right, so get that content check done, as well as I do have a video with some really easy questions for Wednesday. All right, any questions? It's a lot, I understand. Don't forget that questionnaire that I handed out on the first day. It is due by turning it into me during office hours. Yes, video, and then take that complete incomplete quiz on Moodle. Like the previous one I had you take on Wednesday, last Wednesday.